Look at the latest humanoid robots hitting the market. Sleek designs, smooth skin, human-like proportions. They look incredible in promotional videos. Now look at Atlas. Weird limbs. Exposed cooling fins, joints that make it look part insect, part reptile. Most people assume Boston Dynamics made design compromises or rushed the aesthetics. They are completely wrong. Atlas looks strange for one reason. It was engineered to survive the real world, and that ugly design is exactly why it will outwork every competitor on the market, including Tesla Optimus. Here is the full story. The head of Atlas product development spent 12 years at Apple, leading the entire Mac division. James Kuczynski knows how to make products elegant. He spent over a decade cramming massive computing power into compact Mac chassis and making sure everything worked perfectly right out of the box. If anyone could make a beautiful humanoid robot, it would be him. Yet even he admits he has never built anything more complex than the Atlas head, and he chose to make it look like this. That decision reveals everything about Boston Dynamics' philosophy. The race to build the prettiest robot with smooth skin, graceful hands, and a human-like gait is going nowhere. Most of those machines will stay prototypes. Meanwhile, Atlas, with its weird proportions, will be rolling off Hyundai assembly lines. Why? Because it solves problems competitors have not even realized exist yet. When Atlas was first unveiled, people immediately noticed the legs. Put Atlas next to Optimus, Figure, or Unitree, and they look completely off. They are wider than expected, with an offset that makes them look almost like insect legs. Most people assumed it was a design compromise. It was not. The legs were the biggest concern because they are such an obvious departure from human form. But here is the engineering reality. When your knee bends, it creates a gap in the joint. Robot joints face the same problem. With the sheer power of modern actuators, anything caught in that gap can be crushed, snapped, or even damage the robot itself. That is a serious safety risk for humans working alongside the machine. Boston Dynamics tackled this with a strict rule: a minimum 1-inch clearance in every joint through the entire range of motion. That sounds simple until you realize what it takes. To maintain that gap everywhere, engineers had to rethink the entire design. The limb segments shifted, the legs became wider, and the robot became taller. All the proportions changed because safety came first. If engineers are obsessed with optimization, why not remove some joints altogether and put the robot on wheels? That is exactly what Swiss giant Hexagon did. Their Eon robot has been moving cargo through BMW's Leipzig plant since late 2025. Wheels are faster and use less energy, but only on flat floors and only for certain tasks. Boston Dynamics decided they did not want an electric scooter with arms. They wanted a universal robot. Their calculations showed that a wheeled base becomes less efficient when the robot needs to reach high shelves or handle heavy components. For Atlas, feet are not a luxury. They are the only way to maintain high performance across different environments. The shape of the legs is just the visible part. The real magic is hidden inside. The entire robot runs on just 2 types of motors. Most humanoids use unique actuators for nearly every joint. The hip, knee, shoulder, elbow, and wrist all have their own specific drive systems. That approach is expensive, complicated, and difficult to maintain. Atlas takes a completely different path. When you have a compact, power-dense actuator, you can use the same basic design in multiple locations across the robot. Boston Dynamics designed and stress-tested just 2 actuator types and distributed them throughout the machine. 10 of one type, 13 of the other, and that is the whole robot. But the actuators themselves are anything but ordinary. These drives are incredibly compact and power-dense, reportedly delivering 2 to 5 times the performance of comparable systems. Tesla Optimus has a claimed payload of around 45 pounds. Atlas can operate around the clock with loads roughly 50% heavier. That is a massive difference. Even more importantly, manufacturing. 2 actuator types instead of 15 transforms the production process. The quality control team knows every failure scenario. The supply chain becomes dramatically simpler. Spare parts inventory shrinks. By investing heavily in the actuator, Boston Dynamics simplified everything else. The robot is basically actuators connected by aluminum links. No complicated gearboxes. No hidden hydraulic systems, just motors and metal. The modularity of Atlas goes even further. The left arm and right arm are the exact same part. They are not mirrored, they are identical. You can literally remove an arm from one side and mount it on the other. That means technicians only need to stock a single arm design and 2 motor types. If a robot damages an arm during a shift, a replacement can be installed in minutes and the machine goes straight back to work. Compare that to many competing humanoids, where a failed joint can sideline the entire robot while technicians wait for a specific replacement part. That is the difference between a research prototype and a factory tool. These powerful motors create another challenge: heat. Heat destroys electronics. Boston Dynamics solved the problem with remarkable simplicity. Those ridges running along Atlas's limbs are cooling fins. No bulky liquid cooling systems. No complicated thermal management. Just metal surfaces designed to dissipate heat while also protecting workers from touching hot components. Atlas does have a fan, but only one. While many robots scatter fans throughout the body, Atlas places a single fan in the head. That reduces noise and eliminates extra vents that would otherwise invite factory dust into the machine. According to Boston Dynamics, the robot can operate in temperatures from -20 to +40 degrees Celsius without freezing or overheating. The head remains the most difficult part of Atlas. Inside is enough computing power for real-time AI, reinforcement learning, and 360-degree spatial mapping, all sealed inside an IP67 waterproof housing mounted atop a 6-foot robot that will inevitably fall over. And robots do fall over, constantly. During testing, development, and early deployments, that head must survive every impact. The signature light ring solves another problem entirely. Instead of creepy eyes or fake smiles, it gives Atlas a simple way to communicate with people, signaling awareness without falling into the uncanny valley. Boston Dynamics is one of the few companies willing to say it openly. The human body is not the pinnacle of design. It has limitations, and robots should not inherit them unnecessarily. They are targeting humanoid capability, not humanoid appearance. Half the robots shown at trade shows look impressive in carefully controlled demonstrations. But factory floors are full of heat, dust, unexpected obstacles, and 24-hour operations. That pretty skin quickly becomes a liability. Atlas, meanwhile, can swap its own battery in under 3 minutes and keep working. The robot's modular architecture also allows it to evolve. New task, new requirement. Engineers can replace individual systems without redesigning the entire machine. After 30 years of robotics development, Boston Dynamics understands something many newcomers do not. You never know exactly what problems reality will throw at you, so you build a system that can adapt. Boston Dynamics spent 30 years learning one thing: robots fall down. Atlas was designed around that reality. From a head built to survive repeated impacts, to interchangeable limbs, to a platform centered around 2 thoroughly understood motors, every decision prioritizes reliability. It is not the prettiest robot ever built, but it might just be the first one that actually works.